Greetings everyone, I am Evelyn B. Baron, a 4th year BEd student. Today I am going to discuss about the Earth. So, astronomers have proposed many explanations on how the Earth and the other planets in our solar system originated. They are little more than ingenious conjectures. However, since they are based on insufficient data, though we know little more about the beginnings of the Earth, we know a great deal about our planet's shape, structures, properties, and motions. Now let's talk about the shape of the Earth. The Earth is not a perfect sphere, but is slightly flattened, probably caused by our planet's force of rotation, which deforms the somewhat plastic Earth in the form that is in balance with the forces of rotation and gravity. The diameter of the Earth is about 7,900 miles or 12,700 kilometers from pole to pole and 7,920 miles or 12,700 kilometers around the equator. In recent measurement, Earth is slightly more flattened on the South Pole than on the North Pole, which make it slightly pear-shaped. Now, let's talk about the Earth's mass and density. What is mass? Mass is a constant value as opposed to weight, which is actually a measure of the gravity that changes from place to place. And a sensitive instrument generally used to determine the Earth's surface is called the torsion balance. The attraction of a large ball of known mass to a small ball is compared with the attraction of the Earth to the small ball. According to the recent estimate, the mass of the Earth is 6.59 times 10 to the power of 21 tons or 5.98 times 10 to the power of 21 metric tons. To determine the Earth's density, we divide the mass in grams by the volume in cubic centimeters. The Earth's volume is 1.083 times 10 to the power of 27 cubic centimeter. If we divide 5.98 times 10 to the power of 27 by 1.083 times 10 to the power of 27, we get 5.5 grams per cubic centimeter as the figure of the density of the Earth. If we mix together the air, if we mix together the air, water, and rock of our planet, the mixture would be weigh about 5.5 times the same quantity of the water. That is why the Earth is the densest of all the. Now, let's talk about the gravity and the magnetism on Earth. Sir Isaac Newton universal gravitation states that every particle in the universe attracts every other particles with a force that varies directly as the product of their masses, and inversely as the square of the distance. The term gravity, or more accurately, the terrestrial gravity, is applied to the gravitational force exerted by the Earth. Gravity is the force that pulls all materials towards the center of the Earth. This force becomes smaller as we move away from the center. Weight decreases farther from the center. You will weigh slightly less on the top of the mountain than in a deep valley. In 1600, Sir William Gilbert advanced the idea that the Earth behaves like a huge magnet with north and south poles. When you see a compass, the nodule falls along the lines of the force that run from one magnetic pole to the other. The magnetic poles do not correspond exactly to the geographic poles. Now let's move on to the three parts of the Earth. The Earth is made up of air, water, and solid ground, or as a scientist would say, the atmosphere, the hydrosphere, and the lithosphere. The scientific terms are derived from the Greek roots atmos, which means vapor, hydro, which means water, and lithos, which means stone. Now let's talk about the atmosphere. The air surrounding the Earth is composed of 78% nitrogen, 21% oxygen, and 1% other gases, including the water vapor and the carbon dioxide. Dust is also present. The lower layer of the air envelope is the troposphere. Tropos means chains in Greek. So, troposphere is the region where great changes takes place in the temperature, pressure, and water vapor content of the air. It is the part of the atmosphere where our weather is occur. Troposphere extends to an altitude of about 6 miles or 10 kilometers. At the outer limit of the troposphere, there is a zone of division between the troposphere and the next sphere, called tropopause. The next atmospheric layer, extending from 6 to 25 miles or 10 to 40 kilometers above the Earth's surface, is the stratosphere. Stratosphere is the zone of strange winds known as jet streams. This is the fast-moving currents of air that may reach velocities of 25 miles or 400 kilometers per hour. The temperature in the stratosphere rises from a low of negative 76 degrees Fahrenheit or negative 60 degrees Celsius at an altitude of 6 miles or 10 kilometers to a high of 32 degrees Fahrenheit or 0 degrees Celsius at about 25 miles or 40 kilometers. The next is the mesosphere. Mesosphere reaches from 25 to 44 miles or 40 to about 70 kilometers above our planet's surface. The air of the mesosphere is much thinner than that of the stratosphere. The temperature of the mesosphere ranges from a high of 32 degrees Fahrenheit or 0 degrees Celsius at 25 miles or 40 kilometers elevation to a low of negative 130 degrees Fahrenheit or negative 90 degrees Celsius at about 50 miles or 80 kilometers. Next layer is the thermosphere. Thermosphere is the region of the atmosphere extended from 44 to 250 miles or 70 to 400 kilometers above the Earth, where the air is extremely thin. Because of the exposure to radiation from the space and the sun, many of the molecules and atoms are electrically charged or ionized. Scientists often call these layers the ionosphere. The next layer is the exosphere. Exosphere from 250 miles or 400 kilometers altitude and higher. It is the outermost fringe of the atmosphere. The extremely thin gas there consists chiefly of hydrogen. The exosphere eventually merges with the sun's atmosphere. In the late 1950s, it was discovered that the Earth is encircled by a large belt of radiation. This belt is known as the Van Allen radiation belt, after its discoverer, American scientist James A. Van. The belt begins about 400 miles or 650 kilometers above the Earth and extends out of some 25,000 miles or 40,000 kilometers into space. It is made up of charged particles radiated by the sun and trapped by the Earth's magnetic field. Now let's talk about the hydrosphere. The Earth appears to be the planet that contains large amount of liquid water. About 3/4 of the surface is covered by the oceans. These bodies of water, together with the large inland lakes, contribute great amounts of the water vapor to the air. They play a large part in the atmospheric change that we call weather. The Earth's surface water, almost 96% of the weight, is made up of hydrogen and oxygen. Sodium, chlorine, and many other elements are also found in oceanic waters. The plants and animals found in the sea are an immensely valuable resource. They provide us food, fertilizers, and industrial materials. The ocean is also a vast storehouse of minerals such as common salt or the sodium chloride, magnesium, manganese, gold, iron, copper, uranium, and silver. Some of these, such as salt and magnesium, are obtained from the sea in quantity. Others will no doubt be made available to us. More efficient methods for extracting them are developed. Now let's talk about the lithosphere. The solid part of the earth is made up of three types of rocks: the igneous rock, sedimentary and metamorphic rock, and soil. Soil consists of rock debris combined with the organic materials. The igneous rock is derived from the molten rock producing matter called magma. Sedimentary rock consists principally of rock fragments that have accumulated through untold millennia and have pressed together. The metamorphic rock, it is rise when igneous rock or sedimentary rock becomes altered through changes temperature and pressure and other forces within the earth. Keith E. Boland, a scientist of the University of Sydney in Australia, has presented the following view. The Earth has a solid outer mantle about 1,740 miles or 2,800 kilometers thick. The Earth's crust makes up only a small part of this mantle. It extends only 25 miles or 40 kilometers or so below of the Earth's surface. The core is beneath the mantle with the radius of some 2,200 miles or 3,500 kilometers. It is divided into solid inner core and molten outer core. Now let's talk about the age of the Earth. The most exact method known to science for determining the age of the Earth is based on the study of radioactivity of a certain minerals. In these minerals, one or more chemical elements decay radioactively, that is, their atoms give off very small particles and other radiation. Isotopes, it is radioactive elements that form during radioactive decay process and have different atomic weights, and some of these may be radioactive and undergo change. Each radioactive decay process takes a fixed length of time regardless of the external circumstances, depending on the isotope and its atomic weight. As the elements decay, its quantity in the rock or minerals becomes smaller, while the amount of the element it is changing into becomes greater. Scientists can calculate the age of rock through knowing the decay times of elements and proportion of the elements and their products. Radioactive elements are the isotopes that commonly used to date ancient objects, including rocks and minerals, are the following. First is the carbon-14 or the carbon isotope with atomic weight of 14, ruthenium-87, potassium-40, strontium-90, and uranium-235 and 238. The quantities of the isotopes in a sample are measured by radiation detectors and other methods. The age of the rocks must be based on one or more isotopes. The oldest rock on Earth was formed nearly 4 billion years ago. The planet Earth itself is thought to be about 4.6 billion years old. Now, let's talk about the Earth's motion. The Earth's motion. In ancient times and throughout the Middle Ages, many people believed that the Earth stood motionless. They explained Earth, the succession of day and night, and the changing position of the stars by saying that the Earth was still and that sky somehow moved around the Earth. We learned that the apparent daily movement of the stars in heaven is due to the rotation of the planet about its axis. Earth makes a single complete rotation in exactly 23 hours, 56 minutes, and 4.09 seconds. One of the best proof of the rotation of our planet is the pendulum experiment first performed in 1851 by the French physicist Jean-Bernard Léon Foucault. He suspended a heavy weight at the end of a steel wire which was suspended from the dome of the Panthéon, a public building in Paris. A pin attached to the end of the weight rested on a circular ridge of sand. Foucault set the pendulum swinging. The pendulum moved to and fro in the same plane, and the pin at the end of the weight began to trace lines in the sand. As the pendulum continued to swing, the line followed different directions. There could be only one only direction. Therefore, it must be the range of sand that was turning. Foucault concluded that the Earth is rotating. Foucault's pendulum is the device used that proved the rotation of the Earth. One of the pendulum has been erected in the General Assembly building of the United Nations in New York City. The alteration of day and night is due to the rotation of the Earth about its axis. The Earth's rotation causes air currents to be turned towards the right in the northern hemisphere and to the left in the southern. The Earth's rotation causes air currents to be turned towards the right in the northern hemisphere and to the left in the southern, a phenomenon called Coriolis force. Due to the rotation of the Earth, an interesting effect produced by focusing the camera on the North Star and leaving the shutter open for several hours. The stars will appear not as points but as curved lines. It is because the Earth is rotating on its axis on which the camera rests. Now, let's talk about the yearly motion of the Earth. So, the Earth revolves around the Sun. One complete revolution is equal to 365 days, 6 hours, 9 minutes, and 10 seconds. We have called the sidereal star or the sidereal year when reckoned relative to the position of the stars in space. The orbit of the Earth around the Sun is an ellipse, with the center of the Sun at one of the two foci. Ellipse is the path of a point. The sum of whose distances from two fixed points to foci is constant. The distance of the Earth from the Sun will vary according to its position in its elliptical orbit. At perihelion, or what we call the nearest approach to the Sun, the Earth is some 3 million miles or 4.8 million kilometers closer to the Sun than aphelion, which called when it is farthest away. According to commonly accepted figure, the mean distance is 93 million miles or 149.6 million kilometers. This is often used as the unit length or the astronomical unit or the AU by astronomers for measuring large distances. As the Earth revolves around the Sun, its axis is tilted at the angle of 23.5 degrees from the perpendicular to the plane of its orbit. As a result, the northern hemisphere will be tilted toward the sun in one part of the orbit and away from it in another part, as will the southern hemisphere. This accounts for the fact that days are longer in summer than in winter in the northern hemisphere. In summer months, the hemisphere is tilted towards the sun. The southern hemisphere is tilted away from the sun during that time, and that the northern hemisphere is slanted towards it. Our planet moves at an average speed of about 19 kilometers or 19 miles or 30 kilometers per second along its path around the sun. Sometimes the Earth moves slower and sometimes it moves faster. In its orbit, it also traveled through space at a much faster speed as it follows the sun in its wandering through heavens. The sun revolves around the center of the galaxy called Milky Way, completing a turn in about 2 million years. As a satellite of the sun, the Earth takes part in this journey, maintaining a speed of estimated at 118 to 168 miles or 190 to 270 kilometers per second. Now let's talk about the wobbly motion. So, the Earth wobbles or precesses. Precession is due to the combined effects of the gravitational attraction and the Earth's rotation. The Moon, and to the lesser extent the Sun, is constantly pulling upon the Earth. This effect, combined with the Earth's rotation, causes the axis of our planet to wobble about its center. As it does so, it traces out two cones in space. These cones have their bases in space above the geographic poles. Because of the precession, different stars become our North Stars. The Polaris is the North Star. Alpha Cpi will be nearest the pole in AD 7500, Vega in AD 14,000. Eventually, the full cycle will be completed and Polaris will be the North Star again. And that's all. Thank you.